Hey, welcome back. This is 3.5, Calc 1, working now with implicit differentiation. And the problem here in this section is that it's not always possible to find an explicit form for your particular function. Okay. So first we just want to talk about what is implicit versus explicit. What are we trying to do in each case? Well, we're trying to find derivatives, okay? Let me make sure my speaker's on. Okay, so some examples then. So an example of an implicit formula would be something like this. This is implicit. An example of an explicit formula would be something like this, y equals 6 over x. This is explicit. So the difference is that for explicit, you have y equals something. Okay. You're able to isolate y on one side and put everything else on the other side. Okay. Okay. So let's look at another one. Here's an example: y cubed minus x squared equals 4. Okay, so this thing is written implicitly. The explicit version, we can actually, get this into this. So if you noticed, this implicit form can be written explicitly like this. Again, you could take this implicit form and write it explicitly by solving for y. So you could go like y cubed is 4 plus x squared. And then y will equal the cube root of 4 plus x squared. Right. So another example then, let's see, and this is explicit. Another example, how about x e to the y minus 10x plus 3y is 0. Okay. And of course, again, this is implicit. In the above two examples, we could solve for y, right, and then take the derivative. No big deal. In this example, you would be pretty hard-pressed to find the expression in terms of y. You could pause the video and take a couple minutes and try to solve for y and see what happens, right? So the explicit form, in this case, I just don't know. I do know what it is. But maybe your boss is saying, I need a derivative and I need it now, for whatever, and me being your boss, I guess. For whatever purposes I use derivatives for. I need the derivative and I don't have the explicit form, but you got to find it anyways, right? That's the problem here in this section. Usually you could just solve y equals something, but it's not going to be the case all the time. And in those cases, what do? Well, what you're going to do is pretend y is just some random function and kind of apply the chain rule. So for example, let's see if I can maybe make this more worded. So let's say I had something like f of x equals sine of 3x, right? So to find the derivative, what would you do? Here we go. This is the same as cosine of 3x times the derivative of 3x, right? Times 3x prime, basically. Okay, and figure that out. So cosine of 3x, the derivative of 3x is 3. So my answer would be 3 cosine 3x. Okay, but now instead of that 3x, we kind of have some unknown thing, right? So we kind of have like sine of y. So how do I take the derivative in that case, f prime of x? Well, you're going to basically use the chain rule, right? So it's going to be cosine of y, but then times the derivative of y. The only problem is now we don't really know what y is. So what we're going to have to do is just leave it like that. Okay, leave it like y prime. So let's take a look. Let's get in here and take a closer look, and hopefully it will make more sense. Okay, so this is now doing the implicit differentiation. Okay. Basically, it's just the chain rule. except you don't know what the heck this y thing is, so you're just kind of tacking on a y prime is kind of how you'll end up thinking of it. Okay, so for example, let's take a look at x squared plus y squared equals 9. So this is the equation of a circle. We can solve it explicitly and then look at the derivatives and then compare and contrast. And some of the one of the exercises, I think maybe they'll have us do that. We'll take a look at it. But right now, let's just try it. Okay, so what I'm going to do with this implicit differentiation, its differentiation is normal, so the derivative of x squared is 2x. And the derivative of y squared will be 2y, but then you have to tack on the derivative of y because we don't really know what y is. And then on the right-hand side, the derivative of 9 is 0. So you basically just take the derivative of everything. If you see a y, you're going to have to tack on a y prime because of the chain rule. Okay. At this point, we can actually solve for an explicit formula for the derivative, right? I can take this thing and use some algebra, isolate this guy, and have kind of an answer, a pseudo answer. So it'd be in terms of y, but it turns out that's okay. That's not a big deal. All right, so let's move the x over. So I'll have 2y, y prime equals negative 2x. Okay, and then I'm going to divide both sides by 2y. And you get y prime equals negative 2x over 2y, which is negative x over y. Okay, and that's our derivative. Let's take a look. You know, we might as well investigate the other version of doing this problem. So doing it explicitly now. So if you have x squared plus y squared equals 9, let's compare and contrast, right? So move the x squared over and solve for y, and you end up with two equations, right? You end up with y equals plus square root 9 minus x squared, and y equals minus square root 9 minus x squared. If you were to graph it, the plus square root 9 minus x squared would be the upper hemisphere of a circle. Okay, so that'd be y equals plus square root 9 minus x squared. And then the y equals negative would be the lower hemisphere of the circle. Okay, so y equals negative square root 9 minus x squared. Okay, so anyways, let's get the derivatives, right? So derivative, and I'm going to work over here, so let me section this off. Just getting myself in a room. Let's look at y equals 9 minus x squared, square root of 9 minus x squared. And of course, we can rewrite that to take advantage of the power rule. The derivative, y prime, bring down the 1/2. I'm going to have to do a chain rule on it. Times 9 minus x squared to the negative 1/2 times the derivative of the guts. So that would be negative 2x. And clean it up a bit. And what do we get? So we get negative x all over the square root of 9 minus x squared. So how does that compare to the derivative we found in this example? Well, if you plug y in to this implicit form of the derivative, what do you get? Well, you get what we got by taking the derivative here below. So if you plug the y in, I'll circle the y in some other color, let's say yellow, I guess. If you plug this y into here, you'll get our answer down here. Okay. Let's look at the other version. So y equals negative square root of 9 minus x squared. So y prime will again be negative 1/2 times 9 minus x squared to the negative 1/2 times negative 2x. Okay, and then that will equal x all over the square root of 9 minus x squared. And again, if you were to substitute in the appropriate y expression, which would be this case, into this formula, you would end up with this expression. Okay, so great. It's an interesting thing to do, and yeah. Okay, so let's move on to another example. Okay. Okay, so this one's a bit more complicated because in this case, you're not going to necessarily be able to get the explicit form for the function. Okay, you're not going to be able to get y equals something. So it's a little bit more realistic, and with regards to when you would want to do the implicit differentiation. Okay, so in this case, again, go through and take the derivative as normal, but when you see a y, you're going to always have to tack on a y prime. So the derivative of x cubed is 3x squared, okay, and then plus, or if you'd rather minus, let's go with plus, negative xy. So first I'll leave negative x alone and take the derivative of y. Okay, the derivative of y is 1, but then you have to tack on a y prime. So I'll have y prime. And then take the derivative of negative x, which would be negative 1, times leave y alone. And then plus, derivative of y squared will be 2y, and then you always have to tack on a y prime. And then the derivative of 7 is 0. Okay, clean it up. Then we have to collect all of our y prime terms, excuse me, on one side. We want to solve for y prime. Okay, so I will move everything else to the other side. We'll have 2y, y prime, minus xy prime equals y minus 3x squared. Factor out the y prime. Get 2y minus x equals y minus 3x squared. Then I have to divide both sides by 2y minus x, and I'll have my expression for y prime. Okay. So you may think, oh, this is kind of a bummer because it's not in terms of x. But if you think about the xy plane, you could kind of get an idea of the slope of the tangent line to the curve at any point. So if you, for example, take the point, I don't know, 0, 1, right? So if you have the point 0, 1, you could plug 0, 1 into this expression. It's kind of a multivariable type expression, and you'll get what? You'll get 1 minus 0 all over 2 minus 0, which is 1/2. So at that point, the slope of the tangent line to the curve will have slope 1/2. So you go up 1 over 2, and the slope of the tangent line to the solution will look like that. Okay, so you can imagine the actual curve, I don't know, going maybe something like this or something, who knows, right? Okay, so it does have some power, even though it's not our regular derivative that we're used to dealing with. Okay, let's move on. Getting back to the first example that I showed you back here when I initially introduced the implicit differentiation, or the idea of being implicit, this guy right here. Okay, let's go ahead, and if you tried when I gave it to you to find the explicit solution, you would have failed, right? Let's at least get its derivative. Okay, so let's go down here and take a look at that guy. So we have x e to the y minus 10x plus 3y is 0. And I need to take its derivative. Okay, so first you need a product rule on this part. So leave x alone, and then the derivative of e to the y is e to the y, but you always have to tack on a y prime. Then minus 10, derivative of negative 10x, and then plus 3, derivative of y is 1, then you have to tack on a y prime, equals derivative of 0 is just 0. And then we need to collect the y primes together. I'll move the 10 to the other side. Okay. Whoops, I forgot to do the power rule on the product rule. I screwed that up. Sorry about that. So I just did the first part. So leave x alone times the derivative of e to the y, which is e to the y, and then you have to take on a y prime, and then plus, now you take the derivative of x. Sorry about that. Didn't get my pen to work. There we go. plus the derivative of x is just 1 times then e to the y, and then minus, sorry about that, 10 plus 3y prime, and the derivative of 0, 0. Okay, now we collect the y prime stuff on one side. And then factor out the y prime. And then we can divide both sides to get our y prime isolated. So I got 10 minus e to the y all over x e to the y plus 3. Okay, great stuff. That's pretty much the spiel on that. It's just going to take a bit of practice to get used to it. Maybe one more example before we move on to something a little bit different. Let's try y equals the cosine of x times y. Okay, am I going to be able to pull this off? Let's put x on the other side. That'll make my life a little easier, I think. I don't know. I forget how the problem went. Well, let's try it and see if I can pull it off. Okay, should be able to pull it off, right? All right, so the derivative of y on the left is y prime. On the right, I'll have negative sine of xy, and then times the derivative of xy. So the derivative of xy, first leave x alone, times the derivative of y, which is 1, but then you have to take on y prime. Then plus, take the derivative of x, which is 1, times y. Okay. So I'll have y prime equals, I'll go ahead and distribute. So negative xy prime sine of xy minus y sine of xy. Okay. Get all the y prime stuff on one side. So y prime plus xy prime sine of xy equals negative y sine of xy. Factor out the y prime. So I have 1 plus x sine of xy equals negative y sine of xy. And then divide both sides by the 1 plus x sine of xy. So you get y prime equals negative y sine of xy all over 1 plus x sine of xy. So yeah, it worked. Okay. Let's move on to something a little bit different. One of the advantages of doing this implicit differentiation is going to allow us to figure out the derivatives of inverse functions. Okay. So in particular, let's look at this one. Find the derivative implicitly, and also find the largest interval on which the function is a differentiable function of x. Okay, so so first note, if you have y equals sine inverse of x, then x will equal sine of y. Okay. What we want to do is take the derivative of this thing implicitly, and it's going to allow us to figure out the derivative of sine inverse. Okay, so take the derivative of this implicitly. So on the left-hand side, I'm going to put differentiate implicitly. So on the left-hand side, the derivative of x is just 1. On the right-hand side, the derivative of sine of y is cosine of y times y prime. Okay? And then I can solve for y prime. So y prime will equal 1 all over the cosine of y. Okay? And we want the biggest interval around 0 on which this thing will work. Okay? So in particular, I got to make sure that cosine of y is not equal to 0, and that'll happen when cosine of y will not be 0 when y is in the interval from negative pi over 2 to pi over 2. Okay. not including those endpoints. Okay, so that being said, then we can do some manipulations here with the Pythagorean identity. So also to the side here, I'll write cosine squared y plus sine squared y is equal to 1. And so cosine squared y is equal to 1 minus sine squared y. And then cosine of y is equal to plus or minus square root of 1 minus sine squared y. But on this interval from negative pi over 2 to the pi over 2, if you think about that interval, cosine is positive on that interval. Cosine is positive in the first and fourth quadrants. So cosine of y will be equal to just the square root of 1 minus sine squared y. So I can replace that with 1 minus sine squared y. So what? Well, now look, I have that x is equal to sine y. So I can go and take x and plop them in here and get kind of an algebraic expression for y prime. So this will be the square root of 1 minus x squared. And that turns out to be then the derivative of sine inverse, which is something that we're interested in. Okay, so note, originally y was sine inverse. So we notice hindsight, is 20/20. If y equals sine inverse of x, then y prime is this weird thing 1 over square root of 1 minus x squared. Okay, that derivative we're going to have memorized. Okay. They have a special section just for derivatives of inverses coming up, so we won't worry about that too much yet, but it's on the horizon. Okay, the last section in here then is logarithmic differentiation. Okay, and it's kind of a clever way to find derivatives that may otherwise be excruciatingly painful. First, you'll have to assume some stuff. You assume that y is greater than 0. Because of the domain of the natural log, we're going to be taking the log of both sides. So step 2, you're going to take the log of both sides. And then step 3, differentiate implicitly. Okay, so let's take a look at an example, and we'll leave it at that. This is some sort of example from the book. Y equals x times the square root of x squared plus 1. So this would be kind of annoying to do the old-fashioned way. So we're going to give you another method. Basically take the ln of both sides and then use the natural log properties to expand the natural log on the right. Okay, so you get ln of y equals the ln of x plus the ln of the square root of x squared plus 1, which is the same as x squared plus 1 to the 1/2. And then use the power rule. So you can bring the 1/2 down in front of the natural log using the power rule. So boom, x squared plus 1. And then take the derivative of everything implicitly. So you have, on the left, the derivative of the ln of y is 1 over y, and then you have to tack on a y prime. On the right, derivative of ln of x is 1 over x, plus leave the 1/2 alone, times the derivative of ln of x squared plus 1 is 1 all over the guts, x squared plus 1, times the derivative of the guts, which will be 2x. So we have 1 over y times y prime. Clean it up a little bit. 1 over x plus x all over x squared plus 1. And then solve for y prime. So y prime equals y times 1 over x plus x all over x squared plus 1. The beauty of this method is you can solve you can get this derivative completely in terms of x now, because at the end of the day we have an expression for y, right, way back here. So we're going to be able to borrow this expression, x times the square root of x squared plus 1, and substitute it in here for y and have a nice derivative form. Okay, so y prime will be x times the square root of x squared plus 1 times 1 over x plus x all over x squared plus 1. And if you get really ambitious, you can simplify the heck out of this. Let's see what we get. I'm going to find a common denominator inside there. So for the first term, I'm multiplying top and bottom by x squared plus 1. The second term, I'm multiplying top and bottom by x. Okay. So you'll have, at least in the top, x squared plus 1 plus x squared, which will be 2x squared plus 1. And so we'll go back to my other color. 2x squared plus 1 all over x times x squared plus 1. Right? And then multiply that out. The x's will cancel. And the x squared plus 1 on the outside here is really just parentheses to the 1/2 power. So you can subtract exponents in the denominator. You'll have x squared plus 1 to the 1 minus 1/2, which would be 1/2. And then if you'd rather, you could put a square root there. And that's usually the answer thereafter in the back of the book. Okay. But you could leave it back here as long as you get rid of the y when you go to simplify, because that's part of the point of the logarithmic differentiation. You can replace the y with an expression in terms of x, and not have to worry about some weird derivative with a bunch of y's floating around in it. Okay, so we'll leave it at that, and we'll thank you for watching, and we will see you next time.